4, 5, 6. That is an infinite set of numbers, right? That's an infinite set of numbers. If I visualize that, like if there's a number line, there's 1, there's 2, there's 3. So every point on this number line, right, out this way, that would be an infinite set of numbers. So that gives us some idea of infinity. It's almost like you're counting forever. But it turns out that there's two types of infinity. Okay, there's two types. There's what we call countable, and the other type is called uncountable. All right, so we have a countable infinite and an uncountable infinite. So this set of numbers right here is countable, because you could just start counting, right? You would die before you end your list, but the idea is that you could count forever if you could live forever, right? So what does uncountable infinite mean? So what about, what if I make a list that has every fraction in it? Like, 1 is a fraction, right? 2 is a fraction, 3 is a fraction, but what about all the other fractions? 1/2, 1/3, 1/4, how about like 2/3, 3/5? Everything, every single fraction you could think of is in there. Do you think that would be countable or uncountable? It's actually countable. There's a way that you can count through all the fractions. Okay. So let me ask you this question. Let's say if I take just the numbers between 0 and 1, everything in here, take a number line. All right. What if I close my eyes, I reach in here, and I grab a number off the line? What do you think the odds are that that's a fraction? That it's one of these? Good odds or bad odds or 50-50 odds, or what do you think? Real good? You think slim? You think there's a lot of fractions in here? Yeah. How many fractions are in here? An infinite number of fractions are in here, right? 1/2 is there, 1/3, 1/4, 1/5. But there's a bunch of them, right? I'm saying I close my eyes, I reach, I grab a number. The probability that that's a fraction, good probability or low? You're saying low?
Well, you asked the probability if it was going to be half.
No, not if it's going to be half. Probability that it'll be a fraction, some fraction.
Well, then it'd be a high probability.
Think high probability? What do y'all think? High probability? So you think there's a lot of fractions in there, right? Does anyone think the probability is 100%? Like guaranteed? If I close my eyes, reach in there. Now I'm closing my eyes, right? Okay, so I'm reaching in there. Think it's 100%? I've got to grab a fraction? It's 0. The probability is 0. What? What does that mean?
Are you accounting for I or something?
No imaginary numbers.
Okay.
So you've been taught about numbers, right? And that basically in the real number system, it breaks down to two different numbers, right? In our real number system, you basically have two types of numbers. You have rational numbers. What are rational numbers? Fractions. All the fractions. Okay? And then you have irrational. Can anyone give me an example of an irrational number? I is imaginary. Pi. Oh, pi. Yes, pi is irrational. Any others?
Any improper fractions? Like,
No, improper would be okay. That would still be a, yep.
okay.
E is an irrational number. Square root of 2 is irrational. And then you start really having to dig to think of these, right? Because when you're in school, you're only shown a few of them. So what I'm telling you is that within this little piece of the number line, just right in here, there's an infinite number of fractions in here, but there are also an infinite number of these in here. But there's an uncountable number of infinite number of these in here, and there's a countable number of these. So what that means is this. This is the best analogy I'm ever going to be able to give you, all right? You ever drive out of the city, get away from the city lights? Have you ever looked up at night in the sky and been blown away with how many stars are actually up there when you're away from the city? Okay? So imagine that the number line is like the sky, all right? If you close your eyes and you just point. Let's say you had this perfect pointer that pointed just perfect, right? What do you think the probability is that you would be pointed exactly at a star? High or low?
40%.
How far out are you going?
I mean, like if you could follow this perfect line just straight, and if you could travel down that line, what's the probability you think you're going to run into a star? Yeah, the whole sky. You think it's 100% that I'm going to hit a star? Okay. Then we're still going to have a problem here. Okay? Because really what do you think the probability is that you're going to be pointing into black? Pretty high, right? Really high. The probability that you're pointing exactly at a star is essentially 0. You're most likely going to be pointing at black. And so that's what this number line looks like. There's a bunch of things in here. Stars. That's these guys. All right? But there's more black in here than there is stars. But you can't see the black. It's everywhere and nowhere at the same time. It's weird. So if I close my eyes and do that, I'm going to grab a piece of black. I'm not going to grab a star. But if I open my eyes, I can find the stars. There's the star, and I can go grab it. Does that make sense? So if it doesn't, don't worry about it. This is measure theory stuff. It's not stuff for this class, but I want you to know that there's two types of infinity. That's all I want you to take away from this. There's a countable and uncountable, and that there's a lot more stuff a lot more of these in here than there are these. Most people think it's the other way around. All right, now that we have that out of the way, let's talk about limits at infinity. Next time you're on the beach with your significant other, you can use that little story if you want to kind of soften them up for the evening, get them in the mood, something romantic. No? Not working? All right, here we go. We've already seen that sometimes when we take the limit, we get infinity or negative infinity. Do you remember looking at graphs where our function was doing this? Whoosh, like that, diving up and down? Remember that? So if we look at that one right there, what was the limit here as x approached 0? Infinity, right? So from the left, our function is taken off. Our function here is taking off, right? So we've already had answers where we got infinity as an answer, right? But we needed a picture to be able to get that answer. Here, what we're going to do is, let's look at that one. So what is the limit of this function as x approaches 0? Ignore the vertical red line. Ignore that. It's not supposed to be here. The computer freaked out, didn't know how to graph it. So what is the limit as x approaches 0 here? So from the left, what happens? Negative infinity. From the right, positive infinity. So from the left and the right, are they the same? No, so this limit doesn't exist, right? Okay. But still, the idea here that we can get an answer that's infinity is all I want you to take away from this right now. So now we're going to revisit a definition we had in college algebra, vertical asymptotes. Remember vertical asymptotes? You dealt with these with rational functions. Anytime you had a rational function, you would have vertical asymptotes whenever your denominator was 0 and your numerator was not 0. But now we're going to make a new definition for it. We're going to say, look, if we ever have a function, right? If anyone ever gives us a function, and we take the limit of that function as x approaches some number from the left or from the right, and we get an answer of infinity, or we get an answer of negative infinity, no matter what, if we get infinity from either side, then we are going to say we have an asymptote at that value of a. That's our new definition of asymptotes. And what it does is it allows us to deal with functions that are not rational. In college algebra, you just did rational functions. In pre-cal, you just did trig functions. Now we're saying any function where we have a limit from the left going up or down, or a limit from the right going up or down forever, we will say we have a vertical asymptote there. So, yeah. Let me keep going here. Keep going, keep going. Let's get to some actual problems here. Where are my problems? I think I went too fast. Hold on. Yeah, right here. Yeah, let's just do one. I don't know where my problems went. So let's take a look at the limit as x approaches 2. Let's go from this side. I'm not going to tell you what side that is. Of 1 over x minus 2. I want to know what that limit is. All right. Is it solo? I'm saying that right.
Yeah.
Okay. So first thing we always do when we look at a limit is to let x go to whatever it's going to and see what kind of issue we have, right? That's always the first step. So what happens when you let x approach 2 here? Where does the top go? 1. So it stays 1. And on the bottom? Pardon? 0, right? Oh, you have a glare? Sorry about that. You have 1 over 0, right? Now, what do you do when you have 1 over 0? We haven't talked about that, have we? Remember that sheet that I gave you? That has the table on it? Remember that? We know what to do when we see 0 over 0, right? 0 over 0, algebra, some trick. Maybe it's sine junk over junk. Maybe it's one of those, right? But what about if we get 1 over 0? So take a look at this table, and I want you to look at the bottom right-hand corner, and you're going to see where I wrote fixed plus or minus over, oh wait, no, I'm sorry, I went to the wrong place, bottom left-hand corner, over 0 plus, bottom left-hand corner. And then I have what? Fixed negative over 0 plus. Do y'all see those 4 things? Yes? Do y'all see them? I'm not going to write them all down here, but there's 4 things in the bottom left-hand corner of your table. All right, so would you agree that my numerator is headed towards a fixed number, right? That number is fixed, 1. It's headed towards 1. And do you agree that my bottom is headed towards 0? So that right there tells you that you're in this bottom left-hand thing. What are the only possible answers we can get when we have this situation? Infinity or negative infinity. That's it. We know right now that we have an asymptote here. But we need to figure out if it's positive infinity or negative infinity. That's what we need to determine. Understand? Now, why is this thing doing that? Let's discuss why it's doing that. The numerator wants to be 1, doesn't it? And the denominator wants to do what? Go to 0, right? So what happens if you have a number and you start dividing it by a number that gets smaller? That ratio gets bigger, right? So like if I take 1 and divide it by a half, that's going to be 2. But now let's let this get smaller. What's 1 over 1/10? What's that? 10. That's getting bigger, right? Okay, let's let the denominator get smaller. 1 over 100. That's going to be 100, right? So if your top is staying fixed and your denominator gets small, the ratio explodes and gets big. So this right here wants to become infinite. The only question is it wanting to get infinite positively or negatively? Does that make sense? So the way we determine that is actually kind of weird. We're not going to do any algebra. We're not going to do any sort of tricks or anything. We're going to say to ourselves at this point that we have a fixed positive number on top. Agreed? 1 is positive. Over something that's approaching 0. Now, all I have to determine is whether or not I'm approaching 0 through positive numbers or negative numbers. So remember, if you have the number 0 here, you can either come into 0 this way or this way, right? That way or that way. Those are the 2 directions. So if I told you right now that this was positive, then you'd have a positive over a positive, which is positive. So your answer should be positive infinity. If this is positive over a negative, then you would have negative infinity. Make sense? So how do we determine that? Here's how I determine it. I'm going to show you. Ready? Here's how it goes. What I do is I look at what I'm approaching. What am I approaching? 2. I draw a number line, and I put 2 here. All right? Which side are we coming into 2 from? We're coming in from the right. So if I were to take a number, take numbers as I get closer to 2, can somebody give me an example of a number that would be to the right of 2, but just a little bit bigger than 2? 2.1, 2.01, 2.001, right? Those all are close to 2. Close. So I'm going to go with like 2.01. And remember, we're not going to say, close and near. We're not getting too into that here. But that would be an example of a number that is approaching 2 from the right. Yes? So what would happen if you took this number, 2.01, and you did try and plug it in right here? What would you get? A positive or a negative answer? You get positive, wouldn't you? It would just be a little bit bigger than 0. And if you went even closer, you would still get a positive here, wouldn't you? No matter what you did. So that's it. That's all we have to do is just do a quick little analysis to make sure that we understand that when this gets plugged in here, we're going to get a positive number, and therefore this is approaching 0, right? Approaching 0 through positive numbers. So the answer to this is positive infinity. Is that a question?
What would you get if you put in like 1.99?
I was going to do that. Let's do that. I want to approach 2 from the other side now. So what if I ask, what is the limit as x approaches 2 from the left side this time of that same function? Okay, so different problem, right? So you run through it first and you check. What do we get when we plug in 2? Fixed, positive, over 0, right? And we just need to figure out if that's 0, if we're heading to 0 through positives or negatives. So I'll draw a number line. What number goes on the number line? 2. Which side am I approaching from? The left. And then Jackson gave us an example of a number that's to the left of 2, like 1.99, right? And so if we do 1.99 into here, 1.99 minus 2 would be a little tiny negative number. So we know that we're approaching 0 through negative values. And that means we have a positive number over a negative number, which means our answer is negative infinity. Does that answer your question?
So our answer in this situation would be
Positive infinity, because we're approaching from the right. This one is negative infinity. So last question then, what is this? Limit x approaches 2 of 1 over x minus 2. That doesn't exist. Because the left and right hand limits are going to different infinities. One's going up, the other one's going down. So if you graph this, right, this is a function we would have done in college algebra. This is a rational function. And what I can tell you about this rational function is that 2, I have a vertical asymptote. As I approach 2 from the left, what is it doing? It's going down. As I approach 2 from the right, it's going up, right? So that's the way it's behaving. But we have a vertical asymptote there. All right, that one okay? Let's do another one. How about the limit as x approaches 5 of x minus 7 over 5 minus x cubed? Let's do x approaches 5 from the left on this one. Ronnie. Where's Ronnie? Ronnie, where's the numerator headed? So we're just checking, right? We're just going to plug in. What are we plugging in? 5, right? So we're going to plug in 5. Where's the numerator headed? The top, on the top. -2, okay. Which happens to be a fixed negative number, right? Over. Now the bottom is headed towards 0. right? So from here, we recognize we don't have 0 over 0, right? Don't start trying to do factoring and all that. Don't do that. Right now, we know the answer is either infinity or negative infinity, or it could not exist. I mean, it is possible that it doesn't exist if it's not the same from both sides. So this is fixed and negative over 0, and we just need to figure out if that 0 is positive or negative. Marcus? Marcus? What should I do next, or what do you want to do next, Marcus? What do I do on the last one at this point?
So put 5 on the number line.
Yep, put 5 on number line. And approach, come in from the left. 4.99, something like that. 4.99. And then you think about what would happen if you plug that in, right, to the bottom. And what would happen if you plug 4.99 in here? You get a positive. And then you cube it, right, which should still be positive. So you're going to get a number that's approaching 0, but it's positive. So I can now fill this in with positive. And so what's the answer here? Negative infinity. So, I mean, you can see how, like on a test, there's not a lot of work being done here, right? It's just this little thing right here and like a mental check. All right, I think you could do it from the other side, right? So let me give you something else. Limit, I'll just erase this. How about the limit as x approaches -4 from the left of x plus 1 over 4 plus x. Owen.
Yeah.
Where? Oh, right in front of me. Why that? I was seeing something completely different in your name. All right, Owen, what do you got here?
Plug in the -4.
Okay, so plug in -4. So what are you getting on top? -3. The bottom? 0, right? So you have fixed over 0? Fixed what, though? It's a fixed negative number on top, and on the bottom you've got 0. So you just have to figure out if it's positive or negative. So Owen, what goes next?
That would approach -4.
So I'm doing number line?
Yeah.
Okay, and I'm going to approach -4 from the left. I don't think you're going to mess this up, Owen, but I'm just going to warn you to be careful. Give me a number over there. Good. Okay. -4.1. -4.01. A lot of students right here, what do you think they give me? -3.99. Remember, -3 is over here, right? -3 is here, -5 is here. So if you're on this side, you're bigger but negative, right? So, all right. Now that goes in here, and that would give you what? Some negative number, right? So 4 add to it -4.01, you're going to get a negative number in there. And then that would be negative on the bottom. So what's your answer, Owen? Positive infinity, right? Y'all follow that? The tricky part of this, just be careful with the number line here whenever you're looking at negative numbers from left and right.
Would it be easier to use like a smaller number?
Nope. What do you mean by smaller number?
Like -5?
To me, -5 is just not close enough to -4. I mean, it would work.
I just say that just so you don't confuse myself.
Yeah, I mean, if it helps you, yeah, but I mean, this is that closeness thing that we're talking about. You know, like I think -5 is really far away from -4, but you could argue that -4.01 is really far, right? So, yeah, I mean, if it helps you, just pick anything on this side, plug it in. All right, I want to just, yes?
When we're looking for the 0, if it's plus or minus, on the line, how
from which side we're approaching. So we're approaching from the left. So here's -4. We're coming in from this side. Got it? I'm going to change the problem just slightly. Do the same exact problem. But this time, I'm going to do it just in a different color so you can see how I'm changing it. I'm actually going to take away the left and right. Okay? That means you're going to have to check it from both sides, right? And then I'm going to take this denominator and I'm going to square it. So Jesse, where's Jesse? Jesse, wait. You raised your hand too? No?
No, it's great.
Okay, that was like simultaneous. All right, Jesse, help me out with this one here. Where's the top headed? Where's the bottom headed? I'm headed to -4, right? Up top, where are you headed? -3. Where's your bottom headed? 0, right? Okay. Now that looks like we have fixed what on top? Negative. Then what about the bottom? 0. Now we're supposed to figure out left and right, aren't we? Do we really need to, though? Take a look at this. No matter what happens in here, what are we going to wind up doing after we plug something in there? We're going to square it, right? And that's always going to make the denominator positive, isn't it? I already know the denominator is going to 0. The question was it positive or negative? The fact that I have squared here means it doesn't matter which side I come in from. I mean, you could check it yourself, but we come in from this side, sorry, -4. We would use -4.01. Plug that in there, we get a little negative number, but then square it. We're positive. We come in this way, -3.99. We plug that in there, we get a little positive number, and then we square it. We're still positive. So do you see, I don't need to do this for this problem because of the squared in the bottom. So this is just positive here, no matter what. It means the answer is -infinity. We're done. Make sense? If you want to do this, go for it. It's just going to eat up time, that's all. And I should also mention, about the tests. Part of what I'm testing is your efficiency. So, I give you a number of problems on a test that I believe a Calculus 1 student should be able to do in that amount of time. I know everyone works at a different pace, but that's part of what's tested here. It's like if it takes you 30 minutes to do this problem, like that's going to be a major problem on the test. Okay, so you want to be practicing your homework, getting efficient. You don't want to spend 10 minutes just looking at the problem going, what do I do with this? You want to be to the point where you see it, you recognize it, you know the plan of attack. So usually my rule of thumb is I make the test, I take the test, I time myself, I multiply that by 6, that time by 6, and that's what I expect you can do. And so I think you have 100 minutes for the test, right? So if it's too long, then I'll trim it before I give it to you. So I think it should take you 6 times the amount of time it takes me. I make the problem, so I know exactly what I'm going to do, right? So that's why I use 6. All right. Let's do another one. How about this one? Limit x approaches pi over 2 from the left of tangent of x minus 4 over 1 minus sine x. All right, now this is weird. Jamie? Is it Jamie? Jamie. What's the first thing that we do anytime we see limits? It's the first thing we always do. What have we been doing every single time we've had a limit?
Trying to find the sine x over x and get the one.
Do what?
That-
Fine.
Like the way that we were doing it earlier, where you do
So you're telling me what you're thinking that might be the attack for this. That's my question is, for any limit that you ever see, what's that first step you always want to do? Before you assume that it's any one particular thing, you have to figure out what this limit is doing, right? Is it 0 over 0? Is it 1 over 0? As we're going to see, it can be 0 over 0, infinity over infinity, 0 times infinity, infinity minus infinity, 1 raised to the infinity, 0 to the 0, infinity to 0. There's all these different things it could be. So we can't assume just by looking at this like we have any idea what we're going to do here. We have to try and let x go to pi over 2 first and see what happens. Understand? Okay? So, Danielle, what's the first thing we do every time we see a limit? Yeah, like plug it in and see what it's doing, right? See how it's behaving. James, what do we do? Every time we see a limit, first thing we do?
Figure out what to do.
Yeah, like figure out what's going on, right? It's 3 times we've repeated that, right? 3 times. Don't forget that first step. So what I see happen in tests is that students will go and they'll see this and they'll start thinking automatically of what they're going to do without actually having any idea of what the limit is actually, how it's behaving. So let's check to see what happens if we replace x with pi over 2. Let's not even care about what side we're coming in from. If x goes to pi over 2, tangent of pi over 2. Oh, crap. Oops. That's undefined. Sorry. Cosine. I'll save it. I'll save it there. Whew, sorry about that. We could handle that. We're just not ready for it right now. All right? All right, cosine of pi over 2. So cosine of pi over 2, so pi over 2 is straight up. Cosine is which coordinate? The x coordinate. So we're 0, right? Cosine of pi over 2 is 0. 0 take away 4 is -4. So the top is headed to -4. So automatically, right now, on this table, we are not in the top left corner, right? We're not 0 over 0. Okay. Now, bottom. What is 1 minus, what's sine of pi over 2? So pi over 2, sine is the y coordinate. It's 1, right? So we get 1 minus 1. 1 minus 1 is 0. So we have this thing. And Ian, when you see something like that, you should be thinking that that looks like, yep, good. That's fixed negative over 0 to be determined, right? Okay, so how would you like to do that? This one's a little tricky, but stick with what we've been doing. So,
You can't do it.
yeah, let's try it. Let's see what the number line does. Okay, so what am I going to put on the number line? Pi over 2. Which side are we coming in from? Left side. Okay. Now this is where things are a little different because before we were just plugging the number in and we could just look and see pretty easily if that was going to turn out to be positive or negative. This not so much. We need to know what this number is becoming as we start plugging in numbers that are to the left of pi over 2. So we're trying to figure out what does the sine function do as you come in to the left of pi over 2. So it might be worth it for us to not only do this, but draw the sine function. Okay? So over here, I'm going to draw the sine function. This is pi. This is pi over 2. This is 2 pi, sorry. This is pi over 2. Right? And up here, it's 1 up there, right? So we already knew that. We knew that if you plug pi over 2 in, this was going to turn into a 1. The question was, is this 1 here going to be bigger than that one or smaller as we come in? So imagine we're approaching pi over 2 from the left, right? Which means we're up here on the function. And we're coming into 1, aren't we? We're coming into 1, but are we bigger than 1 or smaller than 1? We're smaller, right? Because we're on that sine curve. We're down here. We're below 1. So as we approach pi over 2 from the left, this thing right here is approaching 1, but it's always smaller than 1, which means 1 minus that number should be positive. Does that make sense? This number right here is going to be smaller than 1. So 1 minus that would be a positive number, so this should be approaching 0 positive. And so the answer to this is negative infinity. All right, let me take a quick look at something here. All right, I'm going to do a quick finish off the attendance here. Marissa? Here, David? Len, is it? What is that? Do you know what that is? Lanissa? Is that right? Yeah. Why did I have trouble with that? Did I say it right in the past? I did. I'm sorry. All right, Yosef? Yusef, yes? David? And Oya? I did that right? 2 Davids? Did we get you both? Jackson, I've got you. Okay, I need to tell you about the homework because you can't do it all. And I just want to verify with the book real quick. So this section 1.6 is in 2 parts, and we've only covered the first part. All right, so on your homework, you should be good to finish up 1.4. That was the one with the sine junk over junk. There's a few problems at the end of 1.4 that involve that. But then skip the homework for 1 to 5, do the homework for 1.6, and for 1.6, where is it? Okay. The infinities start at number 19. So don't do anything past 18. Don't do anything past 18. There's no 18? So just, yeah, stop at 17 for 1.6. So that's only, what, a few problems? And just be aware, the problems in the beginning of that section are different in nature than what we did. They give you a graph and they say, hey, where is this thing going to infinity? Or they give you all these conditions and they ask you to draw a graph. Do you remember when we did that? I gave you conditions and we all had like different pictures of what we drew. But now they throw in this idea of things going to infinity in our graph. So see how those first ones go. This stuff is the stuff that's most important to me. Have a good weekend, right? Is that where we are? Weekend, yeah. Have a good weekend.
No, you forgot to get me.
I did?
It's Michael.
You have a stick, right?
Yeah, you dropped mine.
Oh, and then you picked it up and handed it to me. I must have put it over here.
No, you picked it up and you put it over.
Oh, I must have put it over here. Okay, sorry about that. But you're in here, so we're good. Nobody seems to be missing today. Always be ready for a quiz on Tuesdays.